The topic for today's lecture is rolling motion. We all use wheels. We say two-wheeler, four-wheeler, our bicycles, motorbike, trains, they all have wheels. Wheel is very important. What is so special about wheel? The wheel, when it moves on a road, its motion is rolling motion, and that is why it is important. So, what happens? If you look at cross section, the road is like this, and then the wheel is like this. It has a circular cross section. And then the wheel rotates as well as it moves. The wheel rotates as well as it moves in the forward direction. So, if you consider a spoke of this wheel here, this particular spoke, after some time you will find that the wheel is here, the wheel is here, and this spoke has gone to some other place. So, this is rotation. The spoke was vertical and now it is making some angle with the vertical. So, that is rotation, and then it has moved in the forward direction. So, that is the translation. So, it moves in forward direction as well as it rotates. So, that is how the motion goes, and then this rotation and this translation, they are related by a very special equation, and that is that ensures at this contact the surfaces are not slipping over each other. So, the velocity of this upper surface and velocity of this lower surface must be same in the same direction, so that there is no slipping here. That is the meaning of rolling motion or definition of rolling motion. If it represents a road which is at rest, then this point of the wheel must be at rest. The wheel is going ahead, the wheel is rotating, but this point must remain at rest. There should be no slipping between this surface and this surface. Now, let us do an experiment on rolling. I have a cylinder, a cylindrical tube in fact. This surface is cylindrical, and then this table surface is horizontal flat, and I can put it here, and then I can move it, I can roll this tube in such a fashion that there is no slipping between this table surface and the surface of the tube in contact. It does not rub it like this, or it does not rub it like this. It gently goes and the lower portion remains at rest. So, this is rolling, this is rolling. If I press it with this scale, I am pressing this upper surface with this scale and gently pushing it in forward direction, so that the tube is rotating and going ahead, and the upper surface is definitely moving in forward direction, and the scale is also moving in forward direction, you can see, and there is no slipping between the scale and the tube. It is not rubbing like this, or it is not rubbing like this. So, here these two velocities are same, the velocity of the topmost point and this plastic scale, they are same. So, this tube is rolling on both the surfaces, the surface of the table as well as the surface of the scale. Now, my experiment is this: I keep it here and place this scale here. The zero of this scale is right at the top of this tube. I very gently push it forward, so that there is no slipping between the scale and the tube, and of course there is no slipping between the tube and the table. And let me do it for this much time, so that the other end of the scale is now at the top surface. So here, so how much has the tube moved in the forward direction, and how much has the scale moved in the forward direction? So the scale is the front edge of the scale has reached here, and this tube, the center of the tube has reached here. And when we started the motion, we started when both of these, the front edge of this scale and this center of the tube, they were here at this edge. So how much has the scale moved and how much has the tube moved in forward direction? So you can measure. First tube, you see, is just one scale, length of one scale. It starts from here and the tube reached here. So it's 30 centimeters length of this scale. And then from this point to that point, if you see, it's yet another 30 centimeters. It is yet another 30 centimeters. So the front of the scale or the entire scale has moved through 60 centimeters, but the tube has moved through 30 centimeters. The center of this tube, that or the axis of the tube, that has moved only 30 centimeters, but the scale has moved 60 centimeters. But the velocity of the scale is same at any instant. At any instant, velocity of the scale is same as the velocity of this top surface, because there was no slipping at the top surface also. So the velocity of this top surface, which is also the velocity of the scale, must be double of the velocity of this axis, right? Because the scale's velocity is 2 times the center's velocity, and the scale velocity is same as the velocity of this top surface. So in this condition, if this center is moving with some velocity, say Vc, V center, then at this time this top is moving with a velocity which is 2 times Vc. So this is moving with velocity Vc, and this is moving with a velocity 2 times Vc. Whichever point is at the top and at a given instant, that must move with this velocity. In fact, you can generalize, you can always say that what is omega here, this angle which has been rotated in some time. So omega is delta theta over delta t, that is omega, and you take any point on this object, any point anywhere on this object, and you can call this vector as r vector, this vector as r vector, and then the velocity of this is like omega cross r, and omega is, remember, if it is going this way, omega is in the inside the board. So this will be perpendicular to this line, and its magnitude will be omega into r. So here this r is 2 times the radius. For this point, this r is 2 times the radius, so it is omega times 2r, whereas for the center this is only r, so it is omega times r. This velocity is omega times r, and this velocity is omega times 2r, and therefore velocity of the topmost point is double velocity of the center. In fact, you can do this experiment in a very simple manner. You really don't need the table and the scale and all that. Use your 2 hands. So if I place this cylindrical object here at this this place on my palm, and place the other hand like this. So, look at the motion of this finger which is in contact with the top surface, and I will not allow it to slip like this, okay. And I will roll this tube on my left hand and also on the right hand also. So, look at the motion of the tube and motion of my fingers, these fingers which are at the which are in contact with the top surface. So, how much has the tube moved? The tube started from here and it reached here. So, the length moved by the tube is this much, length of this palm. And how much these fingers have moved? The fingers started from here, the fingers started from here, and where are the fingers now? The fingers have gone here, and it is just length of two palms, one palm is here and one palm is here. So, the distance covered by these fingers is double the distance covered by the center or the axis of the tube, and that shows that the top surface has double the velocity than the axis points. So, in our next experiment, I will be looking at the motion of balls, spherical balls or maybe some other shapes on an inclined plane. So, to start with, I have this steel ball, and if I place this steel ball here, it rolls and goes down this track. This track is, as you see, it is a PVC channel which is used by electricians. Roughly it is a plane, some deviation because its own weight, but you can ignore that. It is roughly a plane, and on this plane if I place this ball, this ball rolls and comes down. So, I will place these two, this steel ball and this glass ball, they are of different materials, different size. I will place them here. So, they are placed at the same height, and then I will release them by lifting this scale and see what happens. So, they go together. This time a bigger ball, bigger steel ball and that glass ball. So, we place them here and then release and see what happens. Even now it goes together. So, it does not depend on the nature of the ball, it does not depend on the size of the ball, whether it is glass, whether it is steel, whether it is smaller, whether it is larger. In all cases the balls roll at the same speed with the same acceleration. So, it does not depend on mu, it does not depend on r. Let us try to understand why this time taken by the balls to cover that length of the inclined plane does not depend on size of the ball or mass of the ball or material of the ball, friction coefficient between the ball and the track. So, let us do some analysis and try to understand that. So, suppose you have this inclined plane and this angle with the horizontal is theta, and the ball you release from some point and this ball rolls on this inclined plane. So, let us see what are the forces on this ball. The forces will be weight, you can write mg, and the normal force from here, from the contact, that will be normal force here, and then you will have friction by this track. So, you will have some frictional force which is parallel to the surface F, small f. That is all. So, if I write the equation for translation in the direction of the track, the net resultant force will be mg sin theta and minus this friction. That will be mass times acceleration of the center. This is the acceleration of this center of the ball, and therefore, this will decide how much time it will take to come from here to here. Distance is half at square. But then what is this f? What is this f? To get that, you have to also look at this angular acceleration or angular motion and consider the torque about this center of the ball. So, the torque of mg will be 0 because it will be passing through this center. The torque, the torque is defined as r cross f, and this r is the position vector of the point where the force is applied with respect to the point about which the torque is being taken. So, I am taking the torque about this center, and then the force is applied at the center. Therefore, this r is 0 and the torque is 0, and same is true for this n. So, this torque is also 0. Then this small f, this frictional force remains, and because of this the force is applied here. So, this will be the r vector, this will be the r vector, this r vector, and this will be the f vector. So, you can see what is r cross f. This will be the radius r and times this friction. So, f into r. So, this is the torque, and that will be equal to the moment of inertia times the angular acceleration. In this scenario, it is not always true, we will talk about that also. Torque is I times alpha is not always true, but in this scenario it is there. So, the torque is this, and the moment of inertia of this spherical ball about this diameter here, and that will be 2 by 5 mr square. So, that is moment of inertia and times acceleration. And you can cancel one r from the both sides. So, this is 2 by 5 m into r, and alpha will be this AC divided by r. This is the condition for no slipping. Alpha is equal to AC by r, that is the condition for no slipping. Angular velocity is equal to linear velocity divided by r, that is the condition for no slipping. And so, this is 2 by 5 times mass and then acceleration c, and this f you can put here. So, mg sin theta and minus 2 by 5 MAC, that is MAC. So, m cancels out everywhere, g sin theta is equal to this 2 by 5 AC you can add here. So, that will become 7 by 5 AC, and hence the acceleration is 5 by 7 times g sin theta. Now, you can see you do not have mass appearing in this equation, you do not have radius appearing in this equation, and you do not have friction coefficient appearing in this equation. So, the acceleration of the center with which the entire ball seems to come down, that is independent of the nature of the surface, whether it is steel ball or it is glass ball, whether it is a bigger ball, whether it is a smaller ball. So heavy ball, light ball, it is independent of all those things, and therefore it takes the same time. Now let me do the same experiment with two different shapes. One object is disc type and another object is ball type, spherical ball type. And what I will do is, I will put this disc here and ball here. So disc is at front, ball is at rear, and I release it from this position. So you see, they have gone at the same speed. Have they gone with the same speed really? If I put the ball ahead and the disc on the rear, see what happens. So you can see the separation. The ball is moving faster and the disc is moving slower. If the ball is in the rear and the disc is in the front, and ball tries to move faster and the disc is not moving that fast, they go together. But if the ball is on the front, then you can see the separation. Now it is your task to do a similar analysis with the disc type object and come out with the acceleration, compare with this expression written here on the board and verify whether it is as it should be, whether the ball must have larger acceleration than the disc as we have seen here, or it is something else.